Well, it's a very great pleasure to introduce our speaker tonight, Dr. Carrie Anderson, a planetary astronomer at the Goddard Space Flight Center, and also her husband, Joe Helmbold, who's a radio astronomer at the Naval Research Laboratory. Planetary astronomy actually includes moons, and between the two of them, they have this type of planetary astronomy has a distinctive flavor that's not present in any other part of astronomy. It always involves one or more parts of geophysics, or what we started out as geophysics. That includes atmospheric physics and chemistry, the physics and chemistry of ices, usually exotic ices in which organic chemistry plays a role, the physics and chemistry of minerals and rocks, geysers and volcanology, plate tectonics, which used to be called continental drift, the magnetic fields produced by the chaotic electric currents in the interiors of the body, the interactions of those protective magnetic fields with energetic particles from the sun, and what happens when the planet loses those protective magnetic fields, and also exobiology. No other parts of astronomy have those extra disciplines which a planetary astronomy involves. Because of the role of these geophysical type questions, laboratory experiments on exotic variants of terrestrial gases, ices, and other solids play an important role in understanding planets, moons, and smaller orbiting bodies. The current issue of Stardust has a picture of Dr. Anderson working in Goddard's chamber for measuring the properties of exotic ices. A major focus of Dr. Anderson's research is Titan, one of Saturn's moons. It's the most remarkable moon in the solar system. She also uses some rather rare technologies. One is submillimeter astronomy. Submillimeter radiation has wavelengths shorter than radio waves, but longer than infrared. And it uses technologies that have only recently become feasible to use in astronomy. Dr. Anderson.
Thank you. Can you guys hear me okay at this level? Okay, if you need me to raise my voice, just holler it out, okay? And also, if you have questions, you don't have to wait till the very end, just, ask away so we can keep that momentum going, okay? So I'm happy to answer whatever, whenever. So thank you, John, and thank you for inviting me. I'm very happy to be here. And that was a very nice introduction. So I am at Goddard. I'm giving kind of a big picture view of Cassini, some of the really interesting results as I interpret them, although there's many I won't be talking about tonight. I've been with the Cassini team for 13 years, specifically with one of the instruments called CIRS. CIRS is the Composite Infrared Spectrometer. It's the thermal infrared spectrometer on board Cassini. I'm a co-investigator on that team. And so I'll show you at the very end, if you guys want, some of the work I actually do, the science that I do. And it will involve pretty pictures, but it will involve really wonderful spectra. So, okay. So John mentioned Titan, and there she is, beautiful Cassini image. Okay. Can you guys all see? Can we dim these just a tad? Is that possible? To get the contrast? Thanks. Is that okay? You good?
Yeah, that's good.
All right. And I got green, not red, so this should really help. Okay, so I wanted to start out prior to launch. Here's Cassini. And for anyone who hasn't really seen the spacecraft, it's quite large. Here are some guys down here. This is the Huygens probe. It was called the Cassini-Huygens spacecraft. Cassini was the orbiter, Saturn orbiter, and then Huygens was a probe that descended down and landed on Titan's surface. And I'll show you a little bit about that. So there's the probe. Here's a high gain antenna. And 11 of the instruments are on the body of the spacecraft, but the mag boom was the 12th one that you can't really see here. And here's the instrument I'm with. I wanted to point that out. But it was an incredible spacecraft. It was NASA's flagship. That's our top tier of missions, planetary flight missions. A lot of members, we had a lot of European interactions. But so here, for those who don't know, the high gain antenna is how the spacecraft would communicate with Earth. That's how we would downlink our data, and it would uplink new commands that we would send it to do the observations, orbital dynamics, things like that. And it had, it was powered by RTGs. I'm sure a lot of you guys are familiar with that. Radioisotope thermoelectric generators. They basically use plutonium-238, the heat generated from the decay. And so there are two types of engines. We had our main engines, which are down here, and they had a bipropellant system. And I wrote it out for you guys because it's nitrogen tetroxide monomethyl hydrazine. Now this was the bipropellant that we were running out of. And that's ultimately how we decided when to end the mission. We were getting very, very low on this. We had the hydrazine thrusters, you can see here and here, and they just used, we use these for like small, like attitude control, small corrections. And we had a lot of this left over, but the main engines were taking a hit with the fuel at least. So I wanted to start off with the launch. I'll just play about 30 or 40 seconds of it. Beautiful night launch. This happened October 15th, 1997.
T-minus 15 seconds. T-minus 10. 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. Pitch program is in, roll program is in. We have cleared the tower, and the Cassini spacecraft is on its way to Saturn.
That's on YouTube if you guys want to watch it. I still get chills when I watch the launch. It was really, I wasn't there for the launch, but pretty amazing. So once the spacecraft launched, it took 7 years cruise phase to get to Saturn, which is pretty fast considering Saturn's at 10 AU, you know, so it's a good distance. So here we are. Here's a simple schematic demonstrating here's the launch. It was 4 gravity assists. The first was Venus, second was Venus, third was Earth on my birthday. That's kind of neat. And then the big boy we really wanted was Jupiter. And we did a nice assist on by Jupiter. And then that basically slingshot us to Saturn. And then orbit insertion was July 1st, 2004. So 7 years, not too bad. The main engines were turned off during this. We didn't turn them on. And then a few months before orbit insertion, we took one of our first images of Saturn and Titan right there. Very, very, I think that's quite beautiful. But it's going to get a lot better as we get closer. Before orbit insertion, we did a flyby of Phoebe, one of Saturn's moons, and here it is, a nice high image resolution. And this is just, we think it's a captured, the small body scientists think it's a captured primordial object, and you can really tell by how aged it looks. But then, here we are, orbit insertion. So here's a top-down view of what happened as we came in. And so we turned the main engines on right here. We had a 96-minute engine burn. Now, we didn't turn the engines on up to this point, and the high gain antenna was pointed away from Earth. So we didn't know, it was really nerve-wracking, 96 minutes, because we didn't know if we were captured by Saturn's gravity or if it was going to turn into a flyby, which we didn't want, you know, like a Voyager 1 and 2 type of thing. So luckily, it went beautifully, and at the end of this 96-minute burn, the prime mission began. Okay, Titan. As John mentioned, I've been studying Titan for 20 years, and it's an amazing moon. And before I show you and talk about some really, really neat things that came out of Cassini, I want to take you back in time to the first flagship mission that flew by Titan. Who knows what it was? Anybody? Nope.
Pioneer.
Pioneer 11, that's right. This is what Titan looked like, Pioneer 11 flyby, 1979. Now, considering Pioneer didn't have a camera and it didn't have a spectrometer. It had a scanning what was it,
Imaging photopolarimeter.
that's right, imaging photopolarimeter, thank you. And that's all it had, but we still could build up this image. But because of the polarimeter, the scanning polarimeter, we were able to tell with the highest phase angle that there were particulates, solid particulates that are scattering in the atmosphere. And we didn't know where those were coming from, but we knew something very interesting was going on, especially from a moon. There's no moon like Titan in the entire solar system. So a year later, when Voyager 1 flew by, this is what we saw. This is the iconic image of Titan from Voyager. When I close my eyes and I think about Titan, I don't see a Cassini image. I see Voyager 1's image still. I grew up with that, you know? And you can't see much, right? At visible wavelengths, which is what we're looking at, we cannot penetrate through this very thick, smoggy atmosphere. This is the stratospheric aerosol. It's one of the things I studied, the particulates in the stratosphere. It's amazing for its own reason, and you can almost see, this is north, you can almost see the polar hood up here, which is really exciting to study, all the ices and the aerosol structure up here. But you couldn't see the surface, which was unfortunate, because we weren't looking the wavelengths we needed to be looking at to penetrate this, to get down to the surface. But we still learned a lot about Titan from this flyby. The first is, I wanted to show you, I superimpose this. This is just a temperature structure of Titan. Here's temperature, and of course over here is altitude. Pressure would be over here. But the aerosol, stratospheric aerosol, absorbs about 40% of the solar photons that hit it. That is what drives a thermal inversion causing the stratosphere. This is the troposphere, this is the stratosphere, stratopause, mesosphere, okay? So it's extreme. It's the most extreme of any thermal inversion in our solar system at all. And it's mostly from the aerosol doing that. And so one thing you've noticed about Titan, for those who are more familiar with Earth, the tropopause here is at 40 kilometers. The stratopause is at a whopping 300 kilometers. It's very extended relative to Earth. It's much fluffier and extends out. Very exciting atmosphere to study. So that was kind of neat. And even though we couldn't see down to the surface, we had a thermal infrared spectrometer on board called IRIS, the Infrared Interferometer Spectrometer. And from a LIM integration, here's an example from IRIS. This is wave number, far infrared, mid. Microns are up there in wavelength for those who prefer wavelength. But what we saw, this is a LIM integration at about 186 kilometers. So that's like mid stratosphere. What we saw, you can see here, a ton of organic molecules. Diacetylene, cyanogen, methylacetylene, here's cyanoacetylene, diacetylene, and it just, let's see, propane, ethane, ethylene, methane. We have deuterated methane, all kinds of, lots of carbon, a lot of hydrogen, and a lot of nitrogen. Very, very interesting. So even back here from the flyby, we thought, okay, based on all these organic molecules, we think they're going into the formation mechanism, driving the photochemistry to make the aerosol, which is a solid, it's a refractory particulate, organic particulate. And so we learned a lot without being able to see down to the surface.
Excuse me, what is that, like, lighter yellow spot?
Here?
Yeah.
Well, the image resolution isn't great, but really what you're seeing is it's called the north-south asymmetry. So the bottom hemisphere actually is brighter. It's really more like got to be on this angle than the northern hemisphere for this time of season. This one we just came out of northern winter. And the north-south asymmetry is actually, depends on what wavelength you look at, but it's telling you the aerosol, the amount of aerosol in the atmosphere. And so if you're looking in the visible here where it's brighter, the aerosol turns out to be, it has a high scattering albedo. It's a high albedo, and so the more you have of it, the brighter it looks. But if you look like in a methane band, for example, where it's dark, it's going to be a reverse, because you're seeing the methane absorption and you can't see the bright aerosol underneath it. So that's all that's tracking. So when we have seasonal reversal, it's a very slow meridional circulation pattern. A Titan year is about 30 Earth years. You see this reversal in asymmetry pattern. It's really neat. Yeah?
Is the bright spot facing towards Saturn or facing towards the sun, or neither?
That it's not a it doesn't matter if it's like a leading hemisphere or anything like that. It just depends on, it's a seasonal variation following the transport of the aerosol during that slow meridional circulation. So it's just telling you about the aerosol. And it's misleading because it depends what wavelength you're looking at it to understand what's going on. So if this is probably around 0.6 microns, 0.62, you have a continuum window, and so your methane will be buried deeper, and you'll see the aerosol above. And so, yeah, it's just tracking the aerosol as it circulates.
So what causes it to be in that hemisphere at that season?
At that wavelength, right?
Oh,
So
at that
here,
wavelength.
Voyager was just barely into early northern spring. So we're coming out of northern winter, which means the pattern was you had the ascending motion was in your the southern hemisphere, but you had subsidence occurring in our northern hemisphere during winter. And so you had that motion of moving the entire circulation of the moon. And so when this reverses, you have, like right now, today, Titan it's southern summer.
No, go ahead.
Which was actually similar to this, because it was southern summer and northern winter.
So is there one convection cell that goes all the way from pole to pole?
GCM modelers, they don't like it when we say that. There's all these little things, but it depends. If you're at solstice, you can more represent a single cell. If it's at equinox, then you have more ascending at the equator, upwelling, and then downwelling. Dynamicists don't like the downwelling term either, but I like, So you can have a double, and then you can have the single. But that's really simple. And GCM folks, they get it all, and they trace it differently. But that's the general idea, depending on when. So every season's about 7 years when you go from, okay. Okay, so Cassini. Here's what the naked eye would kind of see when you look at Titan, if we were standing there or orbiting ourselves looking at the moon. This is beautiful. This is mid-northern winter when orbit insertion started. North is up, and so you can really see this polar hood here. You guys see that extension where it's kind of hazy looking? Well, there's a lot of organic ices forming up here from vapor condensation. And there's also a detached haze. You kind of see that over here?
Yeah.
There's actually the main haze, which is really what you see. Then there's this really thin, more transparent, less opaque separation, and that has to do with the circulation of the moon. It's very, very exciting to study. One thing we planned with Cassini, though, was we understood with the aerosol, what you're seeing here, that as you go to longer wavelengths past the visible into the near infrared, the optical properties of the aerosol start to change. So it becomes more transparent. And so the further you go in wavelength, meaning you can start to penetrate that atmosphere and see the surface. And we knew that would be the case, and that's exactly what we did when we designed a lot of these instruments to fly. So I'm going to show you what happens when we look in the near infrared. That's the surface of Titan. Just truly beautiful. And what's the first thing you think when you look at the surface?
Looks like the Earth.
Mm-hmm. Yeah. It's an active surface that is replenishing itself. You don't see a lot of cratered, old, nothing's happening, there's impact craters hitting it. You see an active surface. You see these dark lowlands, these bright highlands. And then, as you'll see later with Huygens, we've learned a lot about Titan. There's liquid on the surface. I'll talk about that. There's a lot of parallels to Earth. We have rivers, we have lakes, we have dunes. The troposphere has methane rain, methane clouds, just so it's analogous. We call it Titan's methodological cycle as opposed to Earth's hydrological cycle in the troposphere, that is. So it has a lot of similarities, and yet it has a lot of differences. It's really, really cold on Titan. So water ice on Titan, which is the bulk of the density and the mass of the moon, is water ice. But so the surface, when you see the Huygens image, you'll see when you look down the horizon, it's water ice. It's all like standing on water ice, but it's not water ice like on Earth. It's so cold on Titan that water ice is like granite here. Okay, that's how cold it is. So it's not like you can just melt it. I mean, it's too cold for that. And that really defines these highlands and everything. And then, but with the drainage channel, which I'll show you with the Huygens movie, you can't really see them here, but we know liquids had carved those out over time. So, and it wouldn't be liquid water, most likely be liquid methane that would be running freely on the surface. So the next short movie is about the Huygens probe descending through Titan's atmosphere at a low latitude, about 10 south degrees, so just below the equator, and landed on the surface. This is a spectacular, remarkable thing of anything that's ever happened in the outer solar system. So very exciting. This is all animation, of course, but it took 3 weeks to get to Titan from Cassini when we released it. That's the detached haze layer. Okay, you get real imagery soon. There you go. So watch this region. Those are dark drainage channels. Watch for the shadow of the ocean. So there's that horizon view I was telling you about. See it? So, I'll stop it now. I'll let it finish so you guys can read it. So, pretty remarkable, right? So when you saw that horizon view on the surface, when you saw those pebble size looking like rocks, it's not rocks like we have rocks. I mean, it's not silicate material. It's mostly water ice, and it's probably been contaminated over the years and years and years from the organic residue from the aerosol and also from Titan stratospheric ices. They're organic. That's what I study, and over time they precipitate out onto the surface, and that's where they stay. And so you have this very organic inventory building up. Yeah.
And so, what is the high temperature on Titan?
The warmest?
The warmest?
The stratopause probably, and it depends on the season and the latitude you're looking at.
Right,
Probably
the warmest.
200 Kelvin. Get to 200, maybe 210.
Okay. So that's, I'm trying to translate that to
So-
below zero.
So,
Minus 60.
Yeah.
Minus 60, okay.
And the surface is 92 to 94 Kelvin, so what's that, minus 300, 280, 300? I do Celsius and Kelvin and Fahrenheit. I gotta think about it now, and I gotta convert in my head. I gotta get I'm like, wait, because we don't do Fahrenheit anymore in science. Well, I'm like, wait, Fahrenheit, wait, there's a 9/5 in there, right? Anyway, yeah, it's very cold, but it's truly amazing. And so, okay, let's see. All right, so later on in the mission, this is when we found liquid pooling on the surface. So Huygens landed at a low latitude where it's dry. There's evidence of drainage channels over the history, but they were dried up. But north is kind of this way. The radar instrument, this is a bunch of lakes. There's hundreds of these in Titan's North Polar region. And so over here is a radar image. This is just one example, like Giamare, which is, I think, up here. And here's a comparison, like same size comparison to Lake Superior, okay? But the big difference is Lake Superior is full of liquid water. This is mostly, it's dominated by liquid methane. Ethane, there's probably a little ethane in there. Ethane can exist in liquid form near the surface, and so can propane. But dominantly methane. Methane is the second most abundant atmospheric constituent, the gas in the atmosphere. N2 is first. And so we got a lot of methane on Titan. But yeah, so that's pretty amazing. And so Titan is the only other object, except for Earth, that today has liquid pools on the surface, lakes and seas. So that's pretty amazing, being so far from the sun. Yeah.
Any idea, is there any estimate of depth? I'm guessing they're shallow.
Yeah, and I don't know the numbers. The radar team, they do this, and they mapped out, probably meters, I'm guessing. I don't know, maybe tens of meters. I'll have to look that up, I'm not sure. But my husband was just telling me the other day, did you read a paper or was it an article? Article that they were thinking that the sides, like the slopes of the sides of the lakes were more steep than they would expect for forming these kind of lakes. And so the latest theory, and I haven't read the article yet, but the latest theory was that over the history of Titan, there's been like, N2 like desorbing from the surface, but like popping, almost exploding, somehow contributing to that. So that's interesting. Think about methane, that's really interesting on Titan, is we don't know what the source is of methane. It has to be a subsurface or a surface source of gaseous methane, releasing it into the atmosphere. Eventually it pushes past the cold trap near the triple pause, and eventually circulates up into the atmosphere because it's the photolysis of methane and the dissociation of N2 gas very high up, like the thermosphere altitudes, 1,000 kilometers or so, where you drive the photochemistry to make all the trace organic molecules, your ethane, your HCN, all of those, which ultimately condense out in the stratosphere, forming ice clouds, but also goes into making the photochemical refractory aerosol. So it's a process. So methane's being recycled, and the amount of methane that's in the atmosphere today, if there wasn't a replenishment, would have been broken down, and it would have been, 100 million years, or very, very short lifetime. So that's another interesting thing. How do we get the methane? We don't know yet. So there's theories, but we really don't know. So here's just one I wanted to show you. This is later towards the end of the mission, and these are just tropospheric methane clouds that we've imaged. Here they are. Once again, these are convectively formed clouds. These are not the stratospheric clouds, these are the tropospheric ones. Yeah?
What is the average temperature observed on the lakes?
It would be close to the surface temperature.
Around,
Oh, 94 Kelvin.
I just checked, it's like methane melting point is about 90 Kelvin.
Yeah, so methane is, so in the troposphere, you condense the methane out and you form clouds, and then you can have methane rain that can rain down on the surface. So you can have, methane can exist in all three forms on Titan's atmosphere: gas, liquid, and solid. But once you get down to the relatively warm surface, you phase change. You'll have a liquid. It'll be in the liquid phase. But what's interesting though is when it's diluted into N2, which is everywhere, 90+%, it affects the saturation vapor, the freezing point, and the melt. That's all affected by methane and other hydrocarbons as well. So. And the surface temperature varies by a few degrees as a function of latitude. So you'll be colder at the winter latitudes and warmer at the lower latitudes and the high southern, like the winter latitudes, or the summer latitudes. Okay, this was one of my favorite images that ISS, that's the camera, took. And this is like mid-2012 or so. This, can you guys see this?
Yeah.
It's kind of like a button. It's hard, I should turn my laptop around so you can see it. But this is near the South Pole, about 85 degrees south, roughly, and it's a cloud. It's very interesting though. The fact is, so the reason it's dark here is because the southern South Polar region is heading into southern winter. It's a few years out. So we're losing the light because we're going into winter. And because this instrument it's a camera, so it's like vis near a little bit, you're looking at reflected solar photons. So you can't see if you're in the dark, right? But right away, because this is bright, we know it's quite high in the atmosphere. Above, it's picking up on the reflected photons from the sun. So without doing any modeling or any analysis of the data, I know it's pretty high. Once you do the analysis, and we realize, I didn't do it, Bob West, he's at JPL, he's one of the ones that's done a lot of this work. You find out it's about 300 kilometers above the surface. That's the stratopause, pushing the lower mesosphere, okay? Crazy. In order to have something forming, condensing out, an organic, to make a cloud, you gotta be really cold. And we've never observed temperatures that cold at those altitudes to have saturation, like you saturate, there's no way. So it's very interesting. And then around this time, and then more recently, a review paper was kind of done. And here's a VIMS. VIMS is a imaging spectrometer. And so here's the near infrared, 1 to 5 microns, and they detected HCN Ice here and here in it. So people call it the HCN Ice cloud, but it's misleading because although you do see that, we don't know if it's pure HCN or if it's been co-condensed. Co-condensation is something I study that I'm one of the things I'm really known for. But it's still very intriguing. Now, with the thermal infrared spectrometer, for example, we don't need it to be, we see thermal infrared radiation. So we don't need reflected photons. So we can look in the dark, wintertime, it doesn't matter. And that's one of the big pushes, the exciting things about such a spectrometer. Okay, I'm going to switch gears a little bit to Iapetus. I really like Iapetus because it's called the yin and yang moon. I'll show you why in a minute. One thing, it's a very slow rotator, which is strange. It has like a 79-day rotation period. There's this really big ridge right here that we imaged, the camera imaged. And I still don't think people know, scientists know what really formed it. Some thought maybe it was a collapsed ring over time, or maybe it rotated faster earlier in its history, which would cause you to bulge out at the center. But when you look at a different side of it, here you go. You see this? You see this darkness? That's the leading hemisphere of Iapetus, and it's dark as coal. But the trailing hemisphere is bright as snow. Pretty much, maybe not quite that bright. Very intriguing. So it was nicknamed the yin and yang moon. It's intriguing because how can you have the chemical composition of the surface be so different? Usually out at Saturn, you have a lot of water ice everywhere on these icy moons, these airless moons. So one theory that came out of Cassini was it's a term called thermal segregation, and it has to do with Iapetus' very slow rotation. And so the idea is that you have this leading hemisphere. So leading hemisphere, do you guys know what that is? It's the side that drives the orbit around Saturn. So the leading hemisphere is going to get impacted by a lot of energetic particles coming out of Saturn's magnetic field, its magnetosphere. And so we're thinking what's happening is as this bombardment's happening, it's changing. Think of like the morphology of the ice. So you know what, if you guys ever made snow ice cream, you always want the fluffy ice, right? Or the good skiing ice, the snow, even though I don't ski, but I think you want the nice fluffy stuff, right? Well, that's normally what you have on a moon like this. But because this leading hemisphere is being bombarded, it's changing the fluffiness to a packed ice, you know, the kind we don't like, the more wetted ice, you know, that we don't like to drive in because you can slip, things like that. So because of that, it affects how it heats and how it cools. So it takes long, so by heating, it's going to heat more, the darker albedo, compared to the lighter albedo locations on the moon. And so the volatiles can more easily escape and then transport to the lighter. And so the more time goes on, the more extreme albedo changes you see. That's just a theory, though. Enceladus. That's the really exciting moon, right? You guys have all heard of Enceladus? Raise your hand, anybody? Okay, cool. So Enceladus is this really tiny moon, 300-mile diameter. We don't really expect much about Enceladus, but what we found when we started looking at it with Cassini is the North Polar region is over here. Kind of what you'd expect, cratered, old, no resurfacing, nothing exciting going on. Well, airless body people might think there's exciting stuff going on, but in the South Polar region, it looks different, right? Very different. You don't see the cratering, but you see this resurfacing, and what really stands out are these things. These cracks in the surface. Those are nicknamed the tiger stripes. And so what we found was when the sun was, it's called a backlit image from the sun. So the sun's behind Enceladus, backlighting it, and so we saw material jetting out from those cracks in the surface. And that's really exciting because that means these are jetting out and they're condensing to form solid ice particles immediately when you hit vacuum. It's cold. So deep down subsurface, there has to be a liquid reservoir. Probably water, maybe water ammonia, but very intriguing. And so we had about 22, 23 flybys of Enceladus. So we had a mass spectrometer on board called INMS. And here's just one table. So it's an in situ instrument. That means it actually samples the material, brings it in, and analyzes it. And here's just a list of what it's picked up on, okay? This is just one. There's a lot of papers out. All these hydrocarbons, some nitriles, H2S, that's got sulfur. Sulfur is very exciting because it means there could be volcanism down low. You know, we like that kind of thing. And of course, water. Here it measured a mixing ratio is at 90% water. It's the chemical composition. And I think the percentage is up, maybe like up to 96%, since this is an earlier paper in the mission. But very, very exciting. So
That's just giving you the atomic composition.
yeah, so it's giving you the mass to charge. It's a spectrometer. It's a mass spectrometer. Yeah. So it tells you how much, based on the mass. Like N2 is mass 28, so you know it's probably N2. But it's not like an infrared spectrometer, which actually tells you, this is definitely this feature, you know. So it can't identify it that way, but by the mass to charge ratio, you can think it's probably this, it's probably this. Things have distinct ones. But there are overlaps. Sometimes there's an ambiguity, because they have a molecule might have the same mass, and you can't be sure what it is. That's right. Okay, this is the one, I grew up in the 80s, and I played Pacman a lot, and Miss Pacman, I will admit. And so this is Mimas. This is the moon that looks like the Death Star, right? Okay. You guys are a quiet audience. Okay. So that's the Death Star, and here's Tethys over here. These are normal, like, images of the moons, nothing too exciting, right? All right. Now, you see how it looks brighter right here? That just tells us the direction of the sun that's hitting it. So you'd expect it to be warmer here, and then as you go away from that, there'd be a thermal gradation, right? You would cool, okay? Back to the thermal infrared, the spectrometer. When we overlaid a thermal map of these two moons, we didn't see what we expected to see. We saw this.
Wow, different.
So now you see the Pacman, right? Pacman. Here it's like, I imagine the little ghost running from Pacman, you know? So totally unexpected. So basically where it's yellow is warmest, and then where it's bluer is coldest. Here's a temperature range, just so you can see. Very intriguing. And it's back to kind of like, sort of like the Iapetus story, where here, let's just use Mimas for an example. Here is the leading hemisphere, and then the trailing's over here. So as it's heading into the charged particle environment, coming from Saturn's magnetic field, the magnetosphere that it's embedded in, it's being bombarded with these high energy charged particles. And it's altering that fluffy, waterized surface, and it's altering how things are changed. And so you're changing that that structure. Now Iapetus, things are a little different in Iapetus, but here you definitely you're changing that ice to solid versus the fluffy. And so that is affecting the heating and the cooling. And so in this case, it takes longer to heat. You don't heat as rapidly. And that's why it's cooler as you orbit. That's the latest theory on that. And Tethys is a similar a similar pattern as well.
Are they tidally locked to Saturn? Or are they rotating?
They're in resonance, Mimas is in resonance with Titan, I want to say, so they affect each other. Iapetus is tidally locked, but I don't think these are. I'll have to Google it to make sure.
I'm curious because, if it's particles bombarding the leading edge, the leading surface, and changing the composition, but they're actually rotating,
It would
there is
depend.
no,
Well, it would depend on their rotation rate,
yes.
and also it would depend on how long are they buried in the magnetic field. So, for example, Titan spends 90% or so its time in the magnetosphere as it orbits, but it's not always protected by it, and it's getting less from it. That's a good question. Yeah, but I don't know their rotation rates off the top of my head. But yeah, so that's and this is the leading hemisphere. Maybe it is tidally locked. On my phone. I'll look it up.
That's okay, thank you.
I'll look it up. So that's pretty cool. That's pretty neat. Okay, the rings. Let's talk a little bit about the rings. Here it's kind of not quite a cross section, but I wanted to reinforce the large extent of Saturn's ring system. If you look through the telescope, you just see the main rings here, right? A ring through maybe not even the D ring, but these are the classic rings you see, right? Well, this ring here is the E ring, and it's named E ring. Well, this is all because of Enceladus. Totally responsible. As Enceladus orbits Saturn, it's jetting out that water ice, and it causes this ring. And it's diffuse, but it's quite extended. And the distance of this, very diffuse ring system is larger than the extent between Earth and the Moon, just to give you a feel for it. So it's really extensive. Here's a better view of the ring system. This is another backlit image, but this time it's of Saturn. It's just beautiful. The disk obviously was saturated, so we took it, that's why it's blocked out. But you can really see, so you can see this G ring, and you can see the E ring here. And that's Enceladus, guys, all Enceladus. In fact, Enceladus affects a lot of moons, and even Saturn itself. The water that gets to Titan is like 25 Saturn radii away. It's way, it's extended. The way Saturn or Titan gets its water, maybe through the form of OH, is because of Enceladus, the jetting material. And then the OH gets modified, and that's how Titan gets its CO and its CO2. That's at least one theory. So pretty remarkable. And so as the mission progressed and we got towards the end of the mission, we changed our orbits, and so we brought us much closer to the rings. And one of the things that the ring scientists learned, and I put a few up here, so I wanted to reinforce these with you guys, was mass estimate. Very important. And so the ring scientists were able to determine it's a very low mass estimate. I believe it's about 40% the mass of Mimas. Okay? But that actual mass amount combined with the very pristine condition of the ice particles, meaning they weren't dirtied over time by organics and different things dirtying it, implied that the ring system is quite young, 10 to 100 million years old maybe. So think about it. Most of its life, Saturn hasn't had rings. Up until the age of the dinosaurs, it developed its ring system. That's what that's implying. So Saturn is billions of years old, right? So that's really, when you think about it, you're like, wow, it's hard to think about. We could be seeing the ring system in a very temporary time of Saturn's evolution. So it's really neat when you think about it like that. So they're thinking that the rings didn't form with Saturn. When Saturn was forming, in the protoplanetary nebula. And then the other thing about the rings is the gravity from Saturn is constantly pulling them in. So you get like this, I wrote it down, dusty rain coming in, and it's going to be impacting Saturn's ionosphere as it comes in. And if this rate continues, assuming there is no source replacing the rings, like if, let's say, micrometeorites are playing a role, or cometary debris, or something that's providing a source mechanism, if that doesn't exist, then the estimate is about in 300 million years, the rings will be gone. So once again, it makes you think about Saturn a little differently, right? It's kind of neat, yeah.
So, do you have evidence from the Cassini-Huygens mission of this dusty ring of particles?
Well, the rings themselves, they're icy and there's small amounts of dust, but a lot of times folks who work with particulates, they call dust small, like micro, sub-micron size ice particles. They'll call that dust. So it's not necessarily, I mean, I'm sure there's some silicates and things in there, but mostly it's ice. Ice and other things. There's salt, there's organics probably, but mostly water ice.
Yeah, but do they have evidence of them actually falling off?
Yeah, you can detect it. So gravity measurements. So I'll show you, well, I'm not going to talk more about rings, but that's a good question because as we got closer and closer to the rings, we went into 20 orbits. We call them the ring grazing orbits. And then after that, we went into 22 final orbits for the grand finale. And we got so close to the rings, closer than we ever have been, even during orbit insertion. And that's when they made these measurements, and they were able to pick this up and detect it. Good question, and I'll show you in a little bit. I'm almost there, but I'll show you. So yes, they measured it. We had an instrument called the CAPS. Let me see, was it CAPS? There was a couple other, but they're like particle counters. They counted hits. So they gave you a particle size distribution. So you knew you had these submicrons to maybe a few microns in size. They got the nice particle size distribution. Yeah. Okay, a little bit about Saturn. Not much. I don't study Saturn's atmosphere much, but this was just really intriguing, this large storm that the camera caught. Now, Hubble has been observing Saturn's atmosphere for a long time. But this storm, it was an accident. It was really serendipitous that they caught this, because when you're on a mission and doing operations, you're planning things 6 to 9 months out, so you don't know. So it just happened, we just were pointing at Saturn's North Pole. We could have been on the other side looking at the South Pole, you know? But so it worked out really nicely to catch the storm. And it was the largest storm that Saturn atmospheric folks have seen in like 20 years. But what was really intriguing about it was how strong of a storm it was. And the reason I want to show you thermal infrared again, I know I keep waving the Sears flag, but the power behind this is months, even after the imager couldn't see the effect of the storm anymore, the thermal infrared radiation went on for up to like a year. So it was a massive storm event. It started in the tropospheric and it just pushed up into the stratosphere and affected a lot of things, especially the temperature. And so we tracked that in time, almost a year, or maybe a little longer than a year. And this is like the beacon. Originally there were two, they called them two beacons. There were two and they merged. And that was just mapping out the vertical extent of this, the thermal changes that happened from the storm. So pretty traumatic. So that was really neat to be able to watch that kind of unfold with time. Okay, this is those ring grazing orbits I was telling you about as we get towards the end of the mission. okay? So they're the project managers for the entire Cassini mission, but the individual instruments went to the PI or the team-led institution. So for example, Sears was a PI instrument. Mike Flazar was the lead, he's a PI on it, and that's at Goddard. We built it, and then we launched it. And so all the operations routed through us at Goddard for Sears. But other, like, I think Hasse was on the probe. That might have been built in with the mass spectrometer folks. But anyway, so they all went to the institutions. So, so that's why you keep seeing JPL, because they had a great outreach group who put a lot of great video out to really keep the public engaged and educated in this. And I wanted to point out that up until the ring grazing orbits, so this is the end of November 2016. Remember, we started July 1st, 2004. You remember? Yeah, okay, that's right. We kept the spacecraft at the closest, like at perigee, or periaps, I guess, 4 to 6 Saturn radii on purpose, away. We didn't get close to the rings. Why did we avoid them?
We got knocked out.
You don't want to get hit.
The number one thing for our mission was you conserve the spacecraft, no matter what.
Sure.
Period. So we stayed away from, because they're dangerous, you know, the micro, you know. We were just watching, what was it, Apollo 13 the other day? And they were getting hit by the micrometeorites and the impact, the damage it can do. So this was a big deal going into those 20 orbits, you know, getting close, but it's going to get so much better. But before it does, here's some, for all you ring and small moon folks out there. So there's the F ring, and there's Prometheus. And remember with Voyager 1 and Voyager 2, they were pretty far flybys. Voyager 1 was a little closer, was closer to Saturn and Titan, and Voyager 2 was further out because Voyager 2 was the big grand, what was it called? The Grand Tour, right? Saturn, Jupiter, Saturn, Uranus, Neptune. So this was, it's like a Christmas wish item, right, to get this close. So pretty spectacular. Here's Pan. This is what you guys all know, Pan. You're talking about it. This is the Enki Gap. So that's in Saturn's A ring. You can see it scooping out all the material. And look at that. Some say it's a tutu. Some say it's a walnut. I say it's a UFO. It's a tutu, right? So that's really neat. So these ring scientists and the small body scientists, and the moonlet folks, are really studying the sweeping of the material, why you get that ring, you know, and things like that. So very, very exciting science.
That's a real buildup of a ring on the satellite?
Yeah, I mean, it's attached to it, yeah, but it is.
It's not
accretion.
Not an optical...
No, it's real. It's a real thing.
Sure.
And this is just like a glimpse I'm giving you guys of all the amazing, it's just a fantastic mission. Saturn's North Pole. Can you guys see this hexagon here?
Yeah.
So each side, it's a 2D image, so it's hard to think about it, but each side's about the diameter of the Earth. But this is a jet stream, so this is like Mike Flazar, the Sears PI, he's a dynamicist. So he says, it's wave number 6, Carrie, don't you know that? And I'm like, dynamicist, right, jet stream. Okay, got it, you know. Okay, roger that. But that's what it is. This is caused, it's a projection of it, but it's a jet stream effect in the North Polar region. But really breathtaking. So this could never have happened during the main mission, the prime mission. Up until we got really close, we started imaging not just the rings, but also Saturn itself. Really neat. Okay, so on April 21st, 2017, we said goodbye. This was a really sad day. And I remember this day, because I knew what it meant. This was nicknamed the Goodbye Kiss. So what happened was we were getting ready to go into the grand finale, the last 22 orbits of the mission. And on the 22nd orbit, we were uplinking to Cassini, tweaking its trajectory forever. So what would happen is even if we lost contact with the spacecraft would still plunge into Saturn on its last orbit, no matter what. So that's why they named it the Goodbye Kiss. And so T126, it started at T0, so there were 127 Titan flybys. Very, very sad. It was sad. But Also, I probably didn't mention this, but we used Titan, like small gravity assist every time we orbited it, which helped us conserve fuel. So, you know, so that was really neat to do that. Okay, so that was sad, but that started the grand finale, 22 last orbits. So here, can you guys see this blue line here, this curve, I mean? This is the ring grazing one. See where we came? Well, look how things are going to change. So we're going between the planet and that innermost D-ring.
Yeah.
Just remarkable. And we were a little scared, you know, a little nervous, because the ring particles, right? So on the last ring grazing, oh yeah, we picked up a lot of particle hits from the rings getting this close. But this one we thought, oh my God, what are we going to encounter? So it was really exciting, nerve-wracking, but exciting at the same time. Here's the first dive. Here's the reference point as we're diving. And here's the camera view. So you can see a lot of fine structure of the clouds. All right. Why are we rotating? Why is the spacecraft rotating? Who knows?
Oh, keep your antenna pointing.
No, that's good, but no, not.
Okay.
It has to do with the high gain antenna, but we rotated because we used it as a shield. For the bust of the instrument, for the main instrument complement to protect it as we went through that gap between the rings and the planet. So when I give talks, I give a lot of talks to elementary age kids, you know, and I'll say, Captain America's shield, right? You know? So I'm like, I have 2 sons, so really cool. So we use it as a shield. And remarkably, it was quiet, relatively so, when we went through. There wasn't a lot going on. There were still some hits, of course. But this is when they started mapping out Saturn's ionosphere, things like that, and really picking up on what was going on. This is when they did a lot of critical planet and ring science during these last 22 orbits. Very, very exciting. For me and Titan, I just kind of waited it out because the type of operations I'll show you guys at the end that I do, I need to be 15, 20,000 kilometers off Titan's limb to do I need that kind of spatial resolution to do the science I do. So this was, I enjoyed it, I waited, I listened, I watched lots of telecons, you know, but pretty neat. And we were successful, very successful. And then,
How sturdy was that antenna? I thought it was just this really flimsy mesh.
no. Well, there was a high gain antenna, and then there was a low gain antenna. Who asked the question? I didn't see. Oh, no. No.
How do you know you had a hit?
I think you were thinking of Galileo at Jupiter.
Galileo was the one that didn't have
Galileo, wasn't it Galileo that had the mesh antenna that didn't
I
open?
thought they were all the antennas
No.
were basically
Yeah.
similar mesh.
No.
Cassini had a solid dish.
Yeah.
Oh,
Yeah.
okay.
Yeah.
because it was X-band, so you can't.
It was
get
X
away with
and
mesh.
yeah, S band and X band. Yeah.
It's less than a centimeter.
What was the period of its orbit?
Galileo had the antenna that only
Yeah, it didn't open
opened
For the last 22,
Yes.
once every 7 days, I want to say. Terrestrial Earth days, yeah. I say that because I have to think of planets when I'm studying a planet, right? So I'm like, oh, is it a Titanian day or is it a anyway? It's what was the
You
question?
talked about hits. How do you know what was the detector for a hit?
There was a particle counter. I keep wanting to think it was CAPS, but that's a plasma spectrometer. There was a dust particle counter, I guess, but dust being any submicron to few microns in size. It could count the hits, so you knew the particle size distribution of what was getting hit.
So it was a hit of a detector. Not
Correct. Yeah.
just- It wasn't just the
Right.
spacecraft being hit and you had a microphone that picked that up.
No. Mm-mm.
Detector itself.
And also, it was a detector. And then also, when we got close to Saturn and we were doing those dives, we got so close, we were in the upper atmosphere, and then we had a couple different spectrometers, and we had the mass spectrometer, which was the biggie. And that's what we learned a lot about the ionospheric environment, things like that was going on because we had the mass spectra. And so that last orbit, the project had to prioritize what would be the instrument that went the longest, and I'm pretty sure it was a mass spectrometer, because that was the most valuable data as we got closer and closer to the planet.
Thank you.
Okay, so this is on the 22nd orbit as we're going towards, well, this actually is probably throughout the movie that was made for the last few looks. The last screenshot you'll see is what, right before the plunge happened. It's tight. It's tight. That's a DIMS image, and I think we hit right around here. But that was documenting where the spacecraft would plunge. And so I think the project always planned on sacrificing the spacecraft. But as we were there 13 years, which was almost half a Titan year or half a Saturn year. A really long time, and we learned a lot, especially about Enceladus. And so as we were running out of that bipropellant, we had to sacrifice the spacecraft and make sure we destroyed it. So there wasn't any chance it would, as it's, if you left it, it would eventually decay its orbit, right? And we didn't want to risk any chance that it would ever hit Enceladus. Because Enceladus, with what we've learned, that is something that may be driving prebiotic, life or habitability, things like that. And so that's ultimately was the decision.
That means you don't want to put Earth microbes on there?
Correct.
Okay,
Correct.
thank you.
Because nowadays, like when you have like a Rex, Osiris Rex, that's bringing a sample of the new back, there was strict contamination protocol that had to be followed. And to try to get all of us, we surprised what we carry. We don't want to contaminate anything. So going to Enceladus, yeah, it's very, yeah.
Did you sterilize the Huygens probe?
People ask me that, and I don't know the answer. I don't think so. I don't think so. I really hope something was done, landing on the surface, but Titan's been, our understanding of Titan has really grown since we've had that mission, But,
We realize in
kinda
most
cool.
spacecraft, we really can't sterilize them.
yeah, yeah.
We can clean them, but we
You can
can't
do your
sterilize
best.
them.
Well, you can heat it.
Yeah.
That's how they sterilize them. They heat them and hope, you gotta make sure you won't, ruin your electronics
Yes.
as you melt to
Not too
sterile.
hot.
But that's there's protocol, and every object in the solar system has its own classification. So Enceladus is high priority. Titan probably is around there now. Maybe Europa might be. Although Europa's surface being bombarded by Jupiter's strong magnetic field, it's super sterile. But it's what's down
Deeply.
below the kilometers and kilometers of that surface, the icy surface that we care about. Okay, so the final hour. Here we are coming in, and so before this we'd go right here, right? That final kiss I was telling you guys about Titan. We landed about 10 north on Saturn. That was the view you just saw in that really sad music move show, That's where we hit. And so I went out to Caltech. I brought my family, it was my kids and my husband. There's hundreds of scientists from across the world who showed up for this, all that had worked at some point on the mission. And this is actually quite funny because Nova did a show on Netflix called Death Dive with Saturn. My brother was watching it one day, and he's like, wait, is that my sister and my nephews? So he takes a screenshot and he emails to me, and I'm like, oh, Nova did a show on Netflix? I'm like, I don't know, And,
PBS too.
I'm in that show. I'm in the PBS show.
Yes.
That one I'm in. So I'm in the first episode. It's called The Planets. If you guys watch it, it's a BBC and Nova did a joint, they worked together on this. It's impressive. In fact, when I watched it, I felt like I was 12 years old again, stargazing with my dad, looking at Saturn, knowing I'm going to be an astronomer one day. That's what it brought me back to. So I really, especially you're young, you should watch that, definitely. So, but I'm in the first episode if you're interested, towards the end, about 40 minutes in. Anyway, yeah, so we all went, and it was like 3:30 in the morning, California time, so we were tired, but we weren't happy because the spacecraft was going to die or anything. That was, you're watching a movie or something, I'm not sure. But I got my iPhone out, back to the X-band, the S-band we were just talking about. I missed the X-band, it dropped out first, but I wanted to show you, especially for the kids, I want to show you, here's the S-band. So that's the spacecraft with the high gain antenna saying, beep, I'm here, downlinking, right? I knew we were close to losing the signal. So a few seconds later, you can see it, less than half strength, right here, and then it was gone. So that's what we considered Cassini's last breath, really. Now what really happened when this was going on is once Cassini hit Saturn's atmosphere, the thrusters, okay? The thrusters were like trying so hard to keep the high gain antenna pointing to Earth to communicate. And they were working as hard as they could, but eventually, didn't take long, the atmospheric drag took over as you're increasing your pressure, too, as you're going deeper, and they couldn't maintain that pointing position. And so at that moment, the spacecraft went into a spin, is what happened. And that is what you're seeing. We lost signal because it's spinning. Now, it only took, I don't know, a few minutes maybe to basically melt, except for the plutonium. I was thinking about the plutonium. I don't know if it ever survived till at some point. I have to look at the pressure diagram for Saturn.
I'm pretty sure those RTGs are designed to survive re-entry.
So, but on Saturn,
Eventually they get crushed in the interior of the planet.
Yeah, right, that's right. But it's kind of neat when you sit back and think about it and go, huh, plutonium, and there's still plutonium on board, so kind of neat. So I guess it all became so Cassini became part of Saturn. That's really sad. I cried, I'll admit it, I cried. It was, because as I talk about it, for 13 years, you get up in the morning, I go to work, between Cassini Cirrus operations and data analysis, downlink the data, check the calibration, I do ray transfer modeling, so I'm a remote sensing person, and that was my life. 13 years looking at upcoming designing. I designed Titan observations, I redesigned a lot of them, I had some new designs. I mean, all of that was it was wonderful. And then it was over. So it's kind of like, it's like losing a family member, but I don't want to sound, like people think it's just a mission, but we scientists, at least, we tend to have difficulty separating out personal and professional. We kind of just do it all, right? So it was losing a big part of me, and that was really hard. But I'm glad we had 13 years. Very glad. The prime mission was only designed for 4, just so you know. So we went into an extended mission, and then an extended mission is what happened. And then before the plunge, we uplinked the final command here in hexadecimal, and it basically said, congratulations to the Cassini Cirrus team for decades of tremendous achievements, and it listed all of our names, which are here. So we all went down with Cassini, right? So this was really nice, and you can kind of see it back here. This is the Sears patch. I just wore my NASA shirt today, but I have Cassini Sears patch stuff, so usually I wear my nice Cassini stuff, but, so that was really nice sentiment that happened. What's next? Okay, that's the end of my overview of the mission. Now, if you're interested, I put together some slides about my science and what I do with Sears science. If you all interested, or?
Yeah, sure.
Yeah? Okay. All right, I thought, let's talk about the stuff I do. So what I'm known for is really Titan is one of the big things I'm known for, but for the stratosphere. Remember the deep thermal inversion I showed you guys of that? A lot of interesting physics and chemistry going on, especially with the composition. The study the gases, but I'm really interested in the particulates. The aerosol, you know, the thing that shrouds the moon completely, and also the ices. Titan has a very complex stratospheric environment when it comes to cloud formation. So I briefly mentioned the methane and N2 get dissociated very high up, right, at homopause 1,000, 1,200 kilometers or so. And then they reform, they form, and they create these other organics, ethane and propane and all kinds of fun stuff. Well, some of those go into the aerosol formation. It's a polymerization that happens. But others eventually suffuse downwards to the stratosphere, where based on the vapor abundances of these compounds and the temperature, they saturate. So what I like to say is the stratosphere is the ultimate sink mechanism for Titan's organic inventory. There's a few exceptions, like ethylene. It gets photolyzed so it won't condense. And it's mainly it, except for propane and ethane won't get to a liquid phase near the surface. But everything else that forms, it's a sink. It's taking it all out. And so you get this very detailed, complex, almost layered stratosphere of all kinds of organics. So we care about organics, right? We care about carbon, we care about nitrogen, hydrogen, things like that. It's not a lot of oxygen. Any of the oxygen is contained in CO and CO2. But Titan's bulk is a lot of water. So if we can melt that water one day, we can get the oxygen and the water that we need with all these organics. So the path is these clouds, these organic clouds form, and eventually they precipitate down and they settle on the surface, the organic. So you're bringing a rich organic inventory to Titan's surface. You're building this up over time. Now the aerosol, you're probably wondering, what about the aerosol? Well, it's quite small, it's relative to the ice particles, but it serves as the heterogeneous nucleation site for the clouds. So that's like on Earth, it's dust and what, bacteria and some other stuff maybe. On Titan, it's the aerosol. So you have that, so you have heterogeneous nucleation, you condense out the different organics, and you form, on average, 2 to 5 vector radii size of particle. That's a lot of mass of organics. Okay, so that's really what I do through observations and modeling and experiments, but I'll get to that. Okay, so I wanted to show you the first 2 clouds I found. This is the Sears far-infrared limb integration. So I like wave number space down here, but if you like wavelength, here you go, okay? So this is LIM, so we're targeting the center of the field of view is sitting at about 121 kilometer tangent height, kind of low stratosphere. And we're integrating, and I want to show you, I've labeled the gases. Here's HCN, hydrogen cyanide, carbon monoxide, methane, diacetylene, this is cyanogen, these sharp features, methylacetylene, this is actually a gas, and cyanoacetylene. Now in this one spectrum, there's 3 stratospheric ice clouds, okay? The first, I'll point out, let me see if I got this was one of my biggest discoveries I ever made, and I called it the 160 inverse centimeter cloud because that's the wave number it peaked at. I'm not too creative when it comes to names like that, but it's quite broad. I won't show you the ray transfer analysis, but it's a very broad. In fact, it's so broad it behaves like a quasi-continuum source. It's very hard to pull out of the data. And this is not how I really discovered it. I'll show you in a minute how I found it. The easy ones to see are the things that ride on the continuum, like the haystack. I called this the haystack about a decade ago. It's actually something that peaks, it's very broad. It's this thing right here. It's immense, and it's cooling like crazy. It's radiating, so it's radiatively cooling. So it affects the thermal structure in Titan's stratosphere. It's a very interesting cloud, but it's vertically restricted, and it's restricted in latitude to winter polar latitudes. This peaks at 221 inverse centimeters, and Voyager 1 Iris first saw this. But in 40 plus years, we have never chemically identified this cloud. It is not a simple, some one compound saturates and you get a cloud. No, it's very, very complex. So I pretty much dedicated my life, I'm going to figure this one out, but I had to build a whole lab to do it. But I'll get back to that in a minute. So the last in this picture is here. This is the new 6 band of cyanoacetylene, HC3, and that's my favorite molecule, just so you know. It's noisy. It's noisy, and we had to de-scope the instrument to save money, so we lost the detector that was supposed to beat down the noise here. But it's okay. You can still see it. That's the ice. Now, with Voyager 1 Iris, the gas here, you see that little like spike? That's the gas peaking at 499 inverse centimeters. The ice is at 506 inverse centimeters. So with Iris, the spectral resolution was too low, it was too degraded. So these were coupled. You couldn't get really a particle size or an abundance of the ice. But with Sears, we had different spectral resolutions. This is our highest, and I can nicely separate out those two. And so because of that, one of my first papers was on how much of it's there, what it vertical looks like, and what the particle size is. It's about 2.5 microns, in case you're wondering. So that was fun. But this is the one I really want to, kind of draw your attention to. This guy here, very, very interesting, harder to find. And I want to show you how I found it. So this is what I was talking about, where I need to be pretty close to Titan with Sears to do these far-infrared targeted limb scans. So this is just mimicking the far-infrared field of view is circular, and we have these designs where they pretty much overlap by about 98, 99%, and we did a very slow 30-minute scan down Titan's, across Titan's limb. So here's 100, this is at one wave number. Tangent height is a function of intensity. Here's where the scan started, near 600 kilometers, very high up. And you can see as we slowly scan, there's not a lot of signal. The density of the atmosphere is too low for me to pick up on it at this wave number. But then as we got deeper, now we're transitioning into the stratosphere, everything takes off. So when I started doing rate transfer modeling of this to try to understand what's in the atmosphere, spatial distributions, things like that, the black curve, can you guys see the black curve here? I couldn't fit the data. I'm looking at, I have everything, I'm trying to simulate the atmosphere, I have everything, the temperature right, collision-induced absorption, but I couldn't fit it. And then I started looking at it. It's interesting with the slope. It's almost like something needs to go in here, vertically restricted, to fix that. So I put a vertically restricted cloud in, generic opacity. I didn't have any optical properties, I didn't know what I was fitting, it doesn't matter. It's an absorber, basically. And when you do that, I got a very nice fit. And that's how I found that cloud. Okay? So, what do I have next? Okay, this is the spectral distribution of that cloud, very broad. That's a spike. We can't take it out in calibration, so just kind of interpolate across that. Very broad. Now, I knew where it was in the atmosphere. It was pretty low. This is a low latitude, 15 south or so latitude, right below the equator. I knew where it was because of the modeling, because you just saw the fits. So what I didn't tell you was all the modeling I do starts at 10 inverse centimeters, which is like 1,000 microns. And I model every 5 wave number up until about 600, so 18 microns or so. But that's how I'm able to build up spectral dependences and things like that. So it was 70 to 90 kilometers or so in the atmosphere where this cloud was at 15 south. And so the next step is you look at saturation vapor curves. One thing I do when I model is I determine what the vertical distributions of the vapors are, all the different organics that I can see in the far infrared. And I knew, based on that, where the curves intersect the temperature profile, is where it's a good first estimate of where the gas will saturate. It's an estimate. And there were 2 that should be condensing out where I needed to put that cloud. One was HCN, and one was HC3N. So hydrogen cyanide and cyanoacetylene. But when I went to some published lab data on the ices, the absorbances, which gives you optical constants, which you want to know, and I plotted them up, it didn't match. Here's the lattice mode, low energy mode of cyanoacetylene. This is a very strong libration mode of HCN. And then over here is a very weak mu7 band of HCN. Doesn't match. So, okay. So what that means is it's not HCN ice plus HC3N ice on top. It's not layered. But I didn't understand. How could it be like that? I know those 2 have to be dominating that chemical composition. I'm certain of it. So I built a lab. It took me a few years, but I did it. Oh, well, an engineer helped me, but here it is. This is my lab at Goddard. I'm not a chemist, but I've kind of become a chemist by necessity. My postdocs are chemists, which is really helpful. And it's really hard to see, but this is a FTS spectrometer, Fourier transform spectrometer. It spans the far to the near infrared, so we go about 50 inverse centimeters to 8,000 or so, which is 200 microns to about 1.25 microns, so a very large spectral expanse. This is, well, here's my turbo pump. It's a big boy. It gets us down to about 10 to the minus 8 torr. It's roughly a millibar, but 10 to the minus 8 millibar, not quite. But so it's very low pressure, high vacuum, low pressure. Here's my cryostat. It's a closed cycle helium cryostat, so I'm able to drop the temperature anywhere from 14K to 350K. And what you really can't see right here is there's a spherical chamber permanently residing inside the sample chamber of my FTS spectrometer. At the end of that cryostat is it's basically called a cold finger. There's a diamond substrate, and that's where we deposit the gases. Here's a mass spectrometer. It's called a QMS, quadruple mass spectrometer. And this is a UV lamp we use to do irradiation. But I had N2. Oh, this is N2 gas because I was trying to purge this to not make ozone, but we made ozone. Ozone is not good. It smells bad. So I had to rethink that design. But anyway, here's the kind of schematic of it. So this is where we put our frozen sample of whatever, HCN, HC3N, whatever we're looking at, in a small dewar under LN2, liquid nitrogen, so it's frozen. We take the dewar away, we sublime it, we warm it up naturally. We fill this entryway, and then we have a variable leak valve, so we open it, and we control the flow and the deposition rate of the gas. There's 2 deposition lines, one here, one here. These are going into that spherical chamber I was telling you guys that are inside the spectrometer sample compartment. And the gases flow, and they deposit on this diamond right here. These are lasers, visible wavelength lasers. While we're depositing, slow deposition, and we're slowly growing the thin ice film thickness. And we're purposely measuring the laser fringes of that because that's what I use to get thickness later down the road. And that's essentially what we do. There's our cryo cooler. So it's compressed helium gas is what it is. And there's our turbo. It's kind of like underneath it. But that's basically the schematic. And so once that was established, and it was a long time coming, but really exciting, we were able to go back. Let me see. Oh, before I show you that, I just want to give you guys an example of what comes out of the lab. For pure HCN Ice, this is what a spectrum looks like. This is the raw data, right, that we record on the spectrometer. And so you can see the large expanse here in wavelength, or wave number. Now, there's a lot of features in here, a lot of combination bands. You can't really see it the way I have it plotted, but we get a lot of information. This, of course, is the strongest. That's the one, these are the 2 bands that cloud hovering at 300 kilometers that Vim saw. These are the 2 ice features. Just to, if you guys think back to those, remember that cloud looked like a button sitting high? There's a problem these are the infrared channel fringes. That's a function of the thickness. The thicker you are, the more you have, the repeatable feature. I correct those. I won't go into any detail, but the end is we get a nice flat spectrum. This is then what I use to compute the optical constants, N's and K's. We all want the optical properties because that's what we feed back into array transfer models to understand those type of properties. You know, that's how you get the scattering effects, things like that, particle size, all that good stuff. So that's kind of the process. Now, what we started doing was looking at co-condensation. So co-condensation is where you take 2 gases or more, you mix them in the gas phase, and then you deposit them on the chamber together. So you're changing something with the ice when you do that. You no longer have, in this case I'm using hydrogen cyanide and cyanogen. These are the 2 columns are just different spectral regions. Here's the far infrared, here's into the mid. And the black curve is when you have layered or co-added HCN and C2N2. So here is the strong HCN libration mode, and here's a very strong new 5 band of cyanogen. And over here you have this weaker band here, the new 4 plus new 5, strong new 2 bend of HCN, and then an unassigned band that we discovered that we don't know what it is. We tried all the different combinations, we don't know what it is yet. Down here, same black trend, black curve's the same, but the pink here shows the co-condensed cyanogen and HCN, and everything changes. Right away you see the strong libration from HCN is damped out. It's almost just squashed. But cyanogen is a beast. We think it's because of that strong CN triple bond. Over here you see the same effect. Look at what it was and look what happens with cyanogen damping those things out. It just takes over HCN. So that's the kind of work we did. And so, that's exactly what I did with HCN and HC3N, right? Back to that 160 inverse centimeter cloud. Remember the spectral dependence. So here's the layered ice with the two compounds. Now I have a postdoc now working on this, so we're just starting. But when I co-condense them, look at the green. Very different. It's not a, we don't know yet. We have to do different deposition temperatures and different mixing ratios. But look at the difference when you mix them, night and day. And the far infrared is where you really want to be looking, because then you're picking up on the low energy bulk, the lattice structure of the material. So imagine the higher energy into the mid-infrared, you might know there's a CNNH or a CNN vibrating, but you don't know from what necessarily. In the far infrared, you know what it's doing, and so you really want to study this, and that's really where we focus in this region. Okay, I'm almost done. I'm not going to talk about all the different clouds, but one of my last discoveries was this cloud I named the HASP cloud, High Altitude South Polar Cloud. Here I'm just illustrating that far infrared field of view, this limb scan, at one wave number, 200 inverse centimeters, that's 50 microns. And I'm giving an example during 85 North T4, that's just the Titan flyby, very early in the mission, northern winter. And you can see as you scan down, there's not a lot of signal until you take off as you get deeper into the stratosphere. Now, there's a lot of clouds in here, but you really can't tell, right? It doesn't look like much. Now, I'm going to fast forward 10 years, heading into southern winter, and I'm going to show you at 75 south, and you see a difference, right? This is a brand new cloud I found without doing any modeling. I just looked at the data. I was so excited, I almost fell out of my chair at work. I want to be honest. It was really exciting to see this. So, that's a new cloud. Okay, so, oh, and for comparison, I want to show you, this is where that VIMS cloud is, up here at 300 kilometers. So you can see, I don't see anything. There's no signal for me with Sears. Here's another look at the tangent high intensity profile at that same latitude I just showed. This is showing 215 inverse centimeters. There's the HASP cloud, that bump, and this dominantly is a haystack. Haystack's a beast. I don't have time to talk about that today, but this is I love talking about the haystack. But I want to focus on this for now. Now, so I do it's fairly easy for me to fit the data, fairly I'll say, and this is what the spectral dependence looks like of the HASP cloud. So just for comparison, here's the 160 cloud. If they're spectrally different, that means they're chemically different. Chemical composition is different. Okay. So here's Titan's thermal profile for that same latitude that I found the HASP cloud out. Now you're probably wondering, what the heck's happening in the stratosphere? This is the stratosphere. You see this, what I call like a second thermal inversion going on up here? That's all due to the stratospheric ice clouds, because they're cooling like mad. And so they're causing that. So normally this should go like this, you know? But it doesn't. You get a significant cooling here. And I mean, my theory is it's from the clouds. But, so I find the HASP cloud, I do the modeling, I know where it vertically resides, but then I go look at those saturation vapor pressures, just like this, for 8, here's an example showing 8 compounds. Benzene, HCN, purple here can't really see is HC3N, diacetylene, and so forth. So when I superimpose here, just to show you guys, this is where the HASP cloud resides. 100 kilometers below it is the haystack. But the HASP cloud, right away, this is what I need to start experimental work. Okay, we got 3 top candidates here to look at. Benzene, HCN, and HC3N. So, we go to the lab. It's really not this fast. It takes a lot longer, but just so you know, lab time is a huge time sink, but it's well worth it. Here's what I derived for the HASP cloud, spectral dependence. Now, this is what pure HCN looks like, HCN Ice looks like. That's that libration mode I keep talking to you guys about. This is noisy because I haven't updated this talk, but this is cyanoacetylene, that's the strong lattice mode. Very different, right? When I co-condense them, we get this aqua curve. Oh, not the chemical composition. Okay, next, HASP cloud. Let's look at, there's cyanoacetylene. Benzene doesn't have any spectral features actually in this region. When I co-condense them, it completely damps out. Benzene is another beast. It's that aromatic, you know, that ring. So it really damps out signal when it's co-mixed with things. It just kind of wants to take over. Okay, next, let's look again at HCN Ice. Benzene. This is when it starts to get very interesting. We first started with the 1-to-1 ratio, 50-50, 50%, 50%. Okay, this is getting very interesting. You can still see the libration mode of HCN, so I knew, let's increase the benzene, which will decrease the HCN in the mixing ratio. So we did it. This is 39% HCN, 61% benzene. Oh, not quite, we're getting close. And the most recent, we're pretty close. This is 21% HCN, 79% benzene. So this is the kind of work we do. We're still doing more analyses like this, and there's a bunch of other clouds I haven't even talked about. I don't have time. But, so, big discovery, super exciting. If you're really interested, I can send you all my papers if you really want them, and I'm happy to do it, because it's fun stuff. So with that, I will end. Thank you.
Take some questions.
Yeah, has there been, maybe not in connection with this mission, search for possible life on Titan? As I understand it, here on Earth, most of the methane comes from decay of organic matter.
And cows.
And cows.
Yeah.
A lot.
But that's organic.
Yeah, the greenhouse gas, right?
Yeah.
Yeah.
No cows on Titan.
No.
Probably
Not
not.
that we know of. You know.
No, but usually methane shows that there's something organic going on, something.
Yeah. Yeah. So methane. Back to we don't know the source of methane on Titan.
Yeah.
So that's a whole mystery. But recently there was an awarded New Frontiers mission from NASA called Dragonfly. And so New Frontiers is a class down from a flagship. It's and it's difficult and expensive to get to Titan. So so this Dragonfly mission I think will launch in 2025 or 6, and it'll get there to Titan in like 2034, I want to say. And it's going to descend on to the surface at low latitudes, and it's like a what is it called? It's not quite a helicopter, but it's there's a name for it, I can't think of it right now. But it's going to hover around very low latitude, and it's going to stop. It's got a mass spectrometer. It's got, I think, a gamma ray or neutron spectrometer as well, and it's going to take samples and try to really understand what's in the regolith, and it'll be able to see if there's any type of venting of gases or anything that's coming up from the surface and things like that. So for life, for Titan, right now that'd be difficult. It's because of the environment. We got a lot of organics, but we don't have any liquid water. Liquid water is also something people follow to track life, to see about. Now, life doesn't mean like us. It could be microbes or something, you know. But what I think on Titan that could be very interesting is with two different things. Number one, if there's any cracks in the surface, and all those organics that layer over time, precipitate out and land on the surface, they could sink down, down deep down to where there's liquid water. Certainly there's liquid water down when you get warm enough. So that's one way to bring organic material down. If that exists. I don't even know if that exists. The other thing is we wait. We won't wait, but, Earth will have to wait for 4 or 5 billion years. Not a big deal, but and for the sun to evolve. And once it goes to red giant phase, it's going to expand. We're going to destroy. Mercury's gone. Venus is gone. Earth, sorry, it's not going to survive. Mars, maybe, but the red giant will be almost out to Earth's orbit. And then I think so the habitable zone. My point is, it's going to push out in the solar system. And back of the envelope calculations, I haven't done any quantitative analysis yet, but by the time the sun gets onto the horizontal branch, I think the habitable zone will probably be in the vicinity of the Saturn system, maybe between Saturn and maybe out to Uranus a little bit. So there's about 1 billion years or so where Titan has a chance. Because what's going to happen is all that solid water ice will melt. Yeah. And it's really interesting to think about it because all the organics are sitting there,
Waiting to be dumped in.
waiting, just begging for a heat source or some energy or something, in liquid water. So, but the question is, there's so much water ice on Titan. I'm worried about a runaway greenhouse effect like on Venus. So it might be the doom and Titan never has a chance because you get this, vicious cycle where you make the water vapor, but it's a greenhouse gas, and then you get this, it keeps warming, keeps melting, and then, or,
Too much of a good thing.
we could have enough melted water to get the liquid water to interact with the organics, and Titan has a chance. So I'm rooting for Titan, but, yeah.
Have you read Stephen Baxter's Titan?
No.
You should, because he covers that exactly.
Oh, okay. These are things I just think about during the day. I wish I had time to do fun reading like that. Who is it?
Stephen Baxter.
Okay, I don't know.
B-A-X-T-E-R, Stephen.
I'll look on for Amazon. I'll look on Amazon. Yep.
Are you involved with this project?
That's for Dragonfly. No, I'm not on the mission. They're targeting, I think it's a lot of surface. It's like a lot of the folks who do the Mars geology, type of, they're not Mars scientists, but it's that type of studying that they're going to do because they're going to sample the surface. I don't think they'll be doing a lot of atmospheric work. If anything, it'll be doing, maybe looking at the humidities, the methane humidities, and things like that. But it's not going to be heavy. I'm a heavy, as you guys have told, as you can tell, I'm a big atmospheric.
You're higher up.
I'm higher up. I'm pure. I want the atmosphere on planets tends to be people's noise if there's a surface, and they want you to get rid of it. Well, I don't want to get rid of it. I want to study it. I want to understand what it means. So.
How long? Do you know how long the prior craft took to get to Saturn? How many of them were there before?
For Cassini?
Yeah, before Cassini.
Well, excuse me. There were 3 flybys before Cassini. There was that Pioneer 11 I was showing you, which is a very distant flyby, so it didn't go into orbit insertion at all. Which didn't, we couldn't really see much. There was Voyager 1, which flew by, and then it only flew by Saturn, and then it went out of the plane of the solar system. And then Voyager 2 flew by, but much more distant, distant from the planet, and because it flew by Jupiter, Saturn, Uranus, and Neptune, and then it left, but it didn't go the same way Voyager 1 went. So then Cassini, and then it was historical because it was the first to go into orbit, and well, pretty remarkable, what we can do. Plus it's a flagship. It's like $1 billion or more now, so,
Does the resurfacing process on Iapetus, does it fluctuate in longitude at all, or is it rigid?
I don't know. I don't study airless bodies, but I thought about pulling some near-infrared spectra to have a look at it. I don't know if Sierra's ever looked at the surface, but I'm becoming more and more interested in exactly what's going on in Iapetus. I just really like that moon, so I might have to dabble a little on a non-atmospheric body. I don't know, but it's a good question. There probably is some variation, I would expect, but it's not enough to where you see. I mean, we saw Iapetus from Voyager 1 and 2 as well, and then we saw it, of course, with Cassini, and it's nothing drastic that's changed to where you have complete transport with the darker and the lighter stuff.
Did anything subtle change around individual terrain features?
I don't know if we have that kind of image resolution to answer that question. Yeah. And then from Earth, I don't think you can't see it. It'd be a point source from Earth. So, anybody else? Yeah.
Have you looked at Titan balloons?
We have. We put together a bunch of us Titan people, got together and submitted a proposal to headquarters, basically. It's a big white paper, is what it is, for a New Frontiers mission. But Titan, so here's the thing. Politics get in the way, okay? So all of astrophysics, earth science, heliophysics, and solar planetary, we all have decadal surveys we follow. So the community gets together every decade, you put in white papers, what you think should be on the list. And for planetary, there's a flagship, there's usually 2 or 3 flagship options. And so if you're not on that list, you're not gonna fly, no matter what. We're lucky to fly anyway, because it's so expensive. So there's flagship list. Then there's New Frontier list. That one, if you don't get on it, sometimes there's 5 or 6 targets in no specific order. If you don't get on that list, you're not going to fly as a New Frontier. So last decadal, Titan was not in the New Frontier list, or the flagship, because this is now Cassini's way before this current decadal. So we proposed trying to get on the New Frontier list for this balloon. That's exactly what we proposed, and it didn't happen because it's very hard to make a New Frontier's budget. I think it's $750 million to go to Titan. But then that one congressman, I don't know who he is, but I'm sure you guys know, decided for the whole ocean world thing, and that Titan and Enceladus were ocean world targets, and they put them on the New Frontiers list. So it really got some people upset because it wasn't fair. I was happy. I'm like, okay. I'm like, hey. So we got that on. That's how this current Dragonfly got picked, because it was on the New Frontier target list, which it originally wasn't on it. So now we're preparing for the next decadal, and we're struggling to get Enceladus on the New Frontiers list. So it's a battle, you know.
If you get a balloon small and light enough, you can just build the damn thing without funding.
You got to get there.
Yeah.
And then you got to communicate the data back to Earth.
Or it's useless.
Yeah, it's a, you know, so I love the idea, and I wholeheartedly support missions to Titan. So, but the good news is, bittersweet, I have 13 years worth of data to unravel still, because I've just scratched the surface, and this is, you guys just got a glimpse of what I've done. I mean, so I'm excited. I've got a lot more data to go through. So, yeah.
Was the haystack, what is that? That wasn't from the MIT Heat Radar Center. What do you mean by the haystack?
I named it that because I named it that. It's a cloud in the stratosphere that peaks at 221 inverse centimeters, and it's very broad, spectrally very broad, and it radiates a lot of intensity. So it's radiating a lot, and it's cooling as it radiates. But it's massive. If you saw that tangent height intensity profile I showed, you could see the effect. I mean, it's a beast. And because it's gone 40 plus years, we don't know what it is. Voyager 1 and 2, IRIS saw it. No one can figure it out. We've condensed everything out in the atmosphere that's in abundance to make it, and nothing matches. And I named it the haystack because it's kind of just sort of symmetric when I think of a haystack, although I don't really think I've ever seen a haystack. Now, I'm a city girl, not a country girl, so, you know. But I named it because we just don't know. And people have picked it up. People are publishing like, oh, Titan's haystack. I love it. So, but with my lab, one thing I want to do is start co-condensing different things, even if they're not in the altitude vicinity of the haystack. I don't think it's farming from vapor condensation. What I didn't talk about was solid-state photochemistry, and I'm sorry, I don't have time. It's another neat thing I found with dicyanoacetylene, kind of cool, but I think the haystack may be forming in a similar fashion, but I need to study it experimentally to quantify it. And it's more like, there's not a direct path to study, it's more like you got to try things out and say, well, where does it go when I do this? So the HASP cloud was easy compared to what the haystack's going to be, but you won't know if you don't try. So it's kind of where I reside.
What is the structure of the haystack? Is it circular like the...
It's restricted. I don't know if it's like homogeneous as a function of longitude, but latitudinally, so it's function of meridionally, it's restricted to about 60 degrees and poleward, depending on if it's northern winter or southern. And what's neat about the haystack is it popped up in Titan's South Polar region near the South Pole before southern winter, with the same spectral dependence. So chemically, it's reforming the same. That blows your mind, because if you're condensing from the vapor, you're not going to get that probably. You're going to get different mixing ratios depending on temperatures and abundances, and that's all driven by the meridional transport, and it's a mess. But the haystack is identical. So that's why it's another reason I think that some other like solid-state photochemical process going on. So there's something that it's using it up to make whatever it is. It's kind of like Earth's polar stratospheric clouds that are responsible for the ozone destruction. That's a little different because that's like a surface heterogeneous process going on. But basically, you need that catalyst of the surface to make the reaction go, and then you release the molecular chlorine, it's photolyzed, you have atomic chlorine that reacts with ozone, and you go drop to O2, right? So it's not on the surface. I think it's buried deep in the particle, but I think it's something similar going on, that we have a repetitive process. Voyager 1 and 2, Iris saw it. Cirrus saw it Northern Winter, and we were there long enough to see it come out of nowhere. Just one day we had it. Well, oh my God, it's in the atmosphere, you know. But spectrally identical. So it's intriguing. So I really can't, it's vertically restricted. It's in Northern Winter though, it was a little higher up in the mid-stratosphere. Southern Winter now, I see it, if you saw it buried deep near 100 kilometers. I'll let you know one day, I hope. I hope.
Let's thank our speaker again.